Hello, today this is the third lecture on atomic term symbol. This lecture is on atomic term symbol and spectra. In this lecture, we will discuss the atomic spectra, especially the sodium spectra in excited state, and we will determine why the two lines are obtained in atomic sodium spectra. Further, in this lecture we will discuss about some selection rules for the atomic spectra. Now the term symbol of excited state of sodium. Here, for example, we will take the sodium atom. The electronic configuration is 3s1. If this s1 electron is promoted to 3p, then in that case n will be 3, s spin will be half, so spin multiplicity will be 2, and if L will be 1, so p term will be there, and the j values will be 2, 3 by 2 and 1 by 2. So in excited state there are two closely spaced levels in the excited state, excited form of sodium with term symbols these and these. So these are the two term symbols of P, or in the excited state, that is 2p half and 2p 3 by 2. This is the diagram for excited state of sodium. So this is the, if the S3s1 electron configuration, and this is the 2p states of when this is excited into the p orbitals. So this is 3 is not the spin multiplicity, but it is the energy level, and this is 3 and 3. The j number is half. Here is the will be half, here will be half, and here will be 3 by 2. So this type of splitting, same L but different J, is called the fine structure. So J, this is the transitions having the different J values are this. So transition will be here to here, that is 2p2, and from here to here, that is 2s. This will be 2p 3 by 2 to this 2s half. So this is the energy difference between these two p orbitals, and this is the energy difference between this energy level and this energy level, this energy level and this energy level. So the two lines are obtained in the excited state of sodium. Now we can calculate the energy of these two states, energy of atomic term symbols, to calculate the energy of single electron atom with quantum numbers L, S and J. So this is the energy for L, S and J is half. H is a Planck's constant, C is the velocity of light, this is I is the coupling constant in atomic spectra, so it is bracket J plus 1 minus L into L plus 1 minus S plus 1. So by putting the all values in this, we can calculate the energy of each levels. Here we have given that 1 electron volt is equal to this centimeter inverse. So this energy and this energy difference is in nanometer. This energy and this energy in also nanometer. So this is the energy formation, energy diagram of these two states. So then the transitions, in allowed transitions there will be high probability, high intensity electric dipole interactions. If that is not allowed, that is forbidden transitions, low probability will be there, weak intensity will be there, and non-electric dipole interaction will be there. Now we are going to discuss about the selection rule for allowed transitions. So first rule is this, that the parity of the upper and the lower layer must be different. So then only then the transition can take place. Now what is the parity? The parity is even if summation of Li is even. The parity is odd if summation of Li is odd. The parity of the term symbol is calculated by this formula. So the summation of Li is the parity, where Li is the orbital quantum number for each electron. In fact, only electrons in odd orbitals contributes to the total parity. Now, when an odd number of electrons in odd orbitals, those four with odd L such as P, that is L is equal to 1, F for L is equal to 3, will make an odd term symbols. So in L is equal to odd and electrons are odd, then will be the parity will be the odd, while even number of electrons in odd orbitals will make the even. If the even number of electrons are present in the odd orbitals, then the parity will be even, irrespective of the number of electrons in even orbitals. So if the orbitals are even, whatever the number of electrons, the parity will be even. Here we can understand more. Odd term symbol will be there. Odd orbitals, thus L is equal to 1, 2, 3, or P, F having odd electrons. So this is the main condition for odd term symbols. These even term symbol will be if the orbitals are odd, having even number of electrons, and even number of electrons having odd or even electrons. So these are the conditions for odd or even parity. When it is odd, when the parity is odd, the parity of the term symbol is indicated by the superscript O, otherwise it is omitted. So this is here in the p orbital, electron is 1, so it is the odd parity, and this odd parity is shown by here O. But this 3p0 is even parity because the orbital is odd but the number of electrons are 2, so it is the even parity. So there is no need to represent here any symbol. Alternatively, parity may be indicated by the subscript G or U standing for G-rayed or un-G-rayed. So this for odd parity. So for odd parity, we will subscribe this U will be used, and for even parity, this G is used. Now the second rule for allowed transition is there should be delta L is equal to plus minus 1. Means the transition can take place from S to P or P to S or P to D or D to P. So this rule is for delta L must be plus minus 1. Third rule is if delta J is equal to 0 or plus minus 1. This is the condition, then the transition can take place. But J is equal to 0 to J is equal to 0 is forbidden. Next, the fourth point is hyper fine splitting due to magnetic coupling of spin and orbital motion of the electrons with the nuclear spin. Magnetic field, in the magnetic field again splitting is there. Isotopic shift sufficient to determine the isotopic ratio. The isotopic shift, we can determine the isotopic ratio by the isotopic shift. Sixth rule, splitting in electric field. This is called the Stark effect, relevant to arc and spark techniques. So this is the splitting, this is called the Stark effect, and the splitting in magnetic field is called the Zeeman effect. In absence of magnetic field, states that differ only by their mj values are degenerate, that is they have equivalent energy. In presence of magnetic field, this is not true anymore. So these are the 3 lectures on atomic term symbol. I hope these are more than sufficient to learn about the atomic term symbol. Now in next we will give the lectures on molecular term symbols. So I hope you will be understand to by seeing these 3 lectures on atomic term symbol. And if there is any problem, you can comment me. I will try to solve